Assalamu alaikum dear students, I hope you all are fine in the best conditions of your health. So today we shall discuss about how to draw the arrow patterns for drawing resonance structures. The key concepts which we shall discuss here today are the resonance structures and the arrow patterns, which we shall discuss in detail, right? So what's resonance? The resonance is just a theoretical concept and it allows us to draw the structures that cannot be otherwise drawn on paper. So in the previous lectures we saw that if we draw the original structure, which is also known as the resonance hybrid or the real structure, on paper, then what happens that we have to violate the rules of valency, right? And we cannot violate those rules. So what we do is that we make use of more than one structure, and each of these structures together, when combined together, they explain the structure of the original molecule, which is called the resonance hybrid, right? So all of these structures which are together explaining the structure of the resonance hybrid, all of these structures are known as the resonance structures. They are also known as the canonical forms, and they are also known as the contributing structures, right? So also we have studied about what are the rules for drawing those resonance structures, but here we will consider the various types of structures which show resonance, and we'll see that how we'll draw the arrow for each of these class. So for convenience, we will divide these types of arrows into 5 different types depending on the system in which resonance is formed, and we'll see that how we can draw the resonance arrow for such structures. So firstly, according to the author of a book which is known as the Textbook of Organic Chemistry, and the name of that author is David Klein, and it's from Johns Hopkins University. So according to David Klein, the resonance is an approach which is used by the chemist to deal with the inadequacy of bond line structures. So what we mean by inadequacy, okay, this is a very broad definition by this author known as his name is David Klein. The inadequacy in the bond line structure means that if we draw the structure in the terms of this bond line formulas, then when we draw the structure for a conjugated system, then we always result in the violation of rules of valency when we explain the structure as the structure is it, right? For example, if we consider the structure of butadiene that was explained in the previous lecture, so if we justify all of the bond lengths, if we justify all of the bond lengths of this butadiene, then it means that all 4 carbons must be doubly bonded, right? So we can explain it like all the 4 bonds of the carbon are doubly bonded because the bond lengths of all carbons are same, and all of these bond lengths are almost equal to the bond length of a double bond, right? So butadiene structure, original structure, should be like that. But the problem is that when we draw the bond line structure, you can easily see that here is violation of valency, and similarly here is also the violation in valency, right? So because of this violation in valency, because of this inadequacy, so we make use of approach known as resonance. Resonance is just a theoretical concept, and normally resonance is used to describe the phenomenon such as the inadequacy or the unjustifiable bond lengths, which we cannot justify if we draw a single structure for conjugated system, right? So we'll see about the resonance and the different concepts that are involved in resonance shortly. So before we go to the resonance, here is about the valence bond theory, right? So valence bond theory, also known as VBD. According to VBD, if more than one Lewis structure can be drawn for a single molecule, right? I say it again, that according to VBD, if you draw more than one Lewis structure for a single molecule, then none of these molecules or none of these structures will represent the true molecule or the true structure, right? And the actual structure, which is the true structure, is the weighted average or intermediate of all these Lewis structure, right? So what do we mean by the weighted average? Weighted average means that structure which is most stable will be more like or will resemble more to the original structure, right? So according to VBD, if we have to draw more than one Lewis structure for a single molecule or an ion, then none of the drawn structure will be the true molecule, and the true molecule or the actual structure will be the weighted average of all the drawn Lewis structure, right? And in such situation, the Lewis structures which we have drawn are known as the contributing structures. They are also known as the resonance structures. Here we will refer to them as resonance structure and abbreviated as RS, or they are also known as the canonical structures. While the true structure or the original structure is known as the resonance hybrid, right? And whatever we have drawn on paper, none of them is the actual structure, or none of them is actually the resonance hybrid, right? And all of the structures we have drawn on paper, they are just trying to explain together the single molecule which is the resonance hybrid. Just for an example, we take the example of this carbonate molecule, right? So this is a carbonate molecule and its formula is CO3. Here you can see that CO3, right? So that's basically a hybrid, and all of these bond lengths, these oxygen carbon bond lengths, are equal, right? And all of these are equal to 1.30 ounce not in actual, right? But this bond length is actually shorter than carbon single bond oxygen, right? So this bond length indicates that none of these bonds is a single bond, and all of these bonds are actually carbon oxygen double bond, right? But if we draw the carbon oxygen double bond, you can just imagine if we have 3 carbon oxygen double bond with this central carbon, then carbon will have 6 bonds, but carbon is actually tetravalent. So how can we explain that? We cannot explain that without violating the rules of valency. So carbon cannot form 6 bonds, it cannot form 5 bonds. The carbon can only form 4 bonds in its neutral state, right? So in this case, we cannot draw just one Lewis structure, but we have to make use of more than one Lewis structure, right? So what we do is that all the CA bonds are of same length, and all of them have same strength. So it say that actually the actual resonance structure we cannot draw on paper, because if we draw that on paper we will violate the rules of valency. So we say that actual resonance structure is a combination, it's a hybrid of all of these structures, right? So you can say here in this case, so we have a carbon double bond oxygen, and here we have oxygen with negative charge, oxygen with negative charge, right? So we are maintaining the 4 valency of this carbon, and we are also satisfying the single valency of this oxygen by putting a negative charge here, right? And in the second situation here, you can say that we have delocalized this electron. So now the formal charge that was previously on this oxygen, now this formal charge has shifted on this oxygen. Similarly in the third structure, so what we are doing is that we are delocalizing this pi electron, and we are also delocalizing those charges. So in this way, all of these oxygens are done by having a double bond. So it's not just a process that double bond is shifting. Actually the double bond has shifted. The double bond is present equally at every place, but the problem is that we cannot show that on paper. That's resonance, right? And all of these structures are Lewis structures, and we have drawn 3 Lewis structures to explain a single structure for carbonate. So according to VBD, since we have used more than one structure to explain the structure of a single molecule or single ion, then none of these Lewis structures is the actual structure, but all of these are the contributing structures, right? And actually this is the Lewis structure. You can say that it's a fractional charges, so all of these are formal charges, right? And all of these electrons and all of these charges are actually delocalized, right? So always remember, we have always resonance when the system is conjugated. Alright, whenever system is conjugated, we have delocalized electron. Whenever we have delocalized electrons, we cannot draw a single structure for explaining the structure of the original molecule, which is also known as the resonance hybrid. Again, we have another example. So this is typical example of benzene. So benzene is a hybrid of two principal calculus structures, right? Both of these are not the original molecule. So both of these are resonance structure or the contributing structures, right? We also have divorce structure, but since their contribution is lower, so we are not showing them here, right? So if you see that when you calculate the carbon-carbon length, right? So the carbon-carbon double bond length for a typical molecule is 1.33 Armstrong, and in case if you are having a carbon-carbon single bond, then the bond length is 1.54 Armstrong. But in case of benzene, all of these 6 carbon-carbon bonds are equal to 1.39 Armstrong, right? So this is slightly larger than carbon-carbon double bond, but this is very, very different. This is very, very smaller than carbon-carbon single bond, right? So we can say, for the safer side, that all of these bonds in benzene are double bond. But if we show them, all of them, as double bond, you can say easily that we will be violating the rules of valency. So we cannot do that, right? So what we do is that we say that actual structure of benzene has all carbons that are equivalent. All of the carbons are sp2, means they are doubly bonded, but we cannot show them on paper like that. So one way is that we put the ring inside benzene that's showing that electrons are equally available throughout all carbons, and the second way is that we make use of resonance. So we say that these are two principal calculus structure, right? Structure 1 and structure 2, and you can easily see that when double bond is here, then there should be a single bond here. But in the second structure, where here is single bond, there will be double bond. So these two structures, if you place them on one another, if you overlap them, they will compensate and will show that every carbon has a double bond. But we cannot draw every carbon with a double bond because we will be violating the valency. So both of these Lewis structures, they are canonical forms, they are contributing structures, and the structure we cannot draw properly, that is the resonance hybrid or the actual structure. Now according to MOT, so previously we used the concept of VBT, now we are using the concept of MOT, so molecular orbital theory. So according to molecular orbital theory, resonance is delocalization of pi electrons or p electrons, right? So the p electrons are not, you can say they are not bonding. According to as per hybridization, they are not unhybridized, right? So the p electrons, if they are non-bonding, right, and the pi electrons or the pi electrons, if they are in conjugation, then they undergo resonance, right, by delocalization of pi electrons. So resonance is basically delocalization, and delocalization of pi electrons or electrons in p orbital. But the compulsion for resonance to occur is that system should be conjugated. So if your system is not conjugate, doesn't matter, it has p electrons or pi electrons, resonance will not occur. Right? So resonance always occur when the system is conjugated. Right? So it's not always that electrons are delocalized as discussed in the previous lecture. So the bond is also delocalized, the electrons are also delocalized, and the charges are also delocalized, right? So any charge, if it's present in that molecule, that will also be delocalized, right? So when we say that's delocalized, the permanent effect, right? We cannot say that the electrons are delocalizing, right? Because the electrons are delocalized. At the same time, the electrons are part of more than one atom, right? So delocalization is not a process. It has happened. It's not a happening. It's what has happened, right? So electrons are already delocalized. The bond has already delocalized. The charge has already delocalized. And the problem is just that we cannot show that on paper, right? So the conjugating p orbitals, they are all parallel, and they are in position to overlap parallel with each other. Right, so by side of the overlap they form pi bond, and they can alternately form pi bond with each other, right? In this way, by their alternating parallel overlaps, the electrons are delocalized. So resonance, since it always occurs in conjugation, right? In conjugation system, it forms a constant channel of electron density. Just like in case of benzene, we form a continuous ring, right? So this continuous ring is showing the continuous general electronic density. and this electronic density is spreading all over the conjugated system. So resonance goes until there is conjugation. So if you have to end resonance, you have to end the conjugation. Right? So once you finish the conjugation, you will finish resonance. Right? So resonance occurs through the molecule until there is a conjugation. Also, resonance is a continuous process, right? Resonance or delocalization is existing in the molecule. It's not that double bond is present at this instant here and the double bond will be present at that instant at the other position. Actually, that double bond is present at all positions at the time, but the problem is simply that we are unable to represent that on paper. Secondly, the resonance or the delocalization, right, only exists as long as the reactive intermediate exists. So in case of reactive intermediates, if there is resonance, then reactive intermediates will have resonance until they remain as reactive intermediate, right? But once the reactive intermediate reacts to form a certain product, the delocalization will vanish. For example, you might have heard of the delocalized 5-member transition state, and that's stabilized because of the delocalization. Similarly, you might have heard of the 3-member transition state, which is stabilized by means of resonance, or 3-member intermediate that's stabilized because of resonance, but their stability will remain until they are reactive intermediates. Once they finish, they end to be reactive intermediates, their delocalization will also vanish, their delocalization also ends. So just for an example, we are taking the example of this cation. So this is an allyl cation, right? So what's an allyl system? If you have a double bond here, and to this double bond we have an sp3 carbon, right? So yeah, if you have an sp2 carbon and to this sp2 carbon we have an sp3 carbon, then this carbon is known as allylic carbon, right? This is allyl carbon and there's a positive charge on it. So this is an allyl cation. So this allyl cation is resonance stabilized. You can say here we have double bond, but in the other resonance structure, so there's no double bond here. So here we have single bond, and in the other resonance structure there's no single bond, there's a double bond here. And also you can say that positive charge is on this carbon and in the other it has shifted on that carbon. So in this example we are shifting the charges as well as the shifting the pi electrons, so it means that both the charges and the pi electrons are delocalized. So this delocalization will continue on. This system will be delocalized until this reactive intermediate reacts, right? So the system is delocalized until that remains a cation. But when this reacts, suppose with a chloride ion, Cl negative, so once it reacts, then the system will not remain delocalized. Now it's an isolated system. Now it's a simple system, right? So the conjugation remains or the delocalization remains in reactive intermediate until they remain the reactive intermediate. Once they cease to be reactive intermediate, the resonance will be finished. The resonance will not be observed in such cases. Right? So far we have discussed about resonance, that resonance is just a theoretical concept. And resonance is used only to describe the structure, so it cannot be otherwise drawn on paper, because if we draw on paper, if we draw the original structure on paper, then we will be violating the rules of Valence. Secondly, we thought that according to VPD, if a structure has to be explained by using more than one Lewis structure, then none of the drawn Lewis structure will be the original structure, and actual structure will be the weighted average of the contributing structures. Then according to MOT, the molecular orbital theory, that delocalization is not happening, it is what has happened. So electrons are already delocalized, the bond is already delocalized, or the charge is already delocalized, right? And lastly, we have seen that reactive intermediates, if they are resonance stabilized, then the resonance stabilization will last as long as the reactive intermediate reacts. So once the reactive intermediate reacts, then resonance stabilization will be gone. Now let's consider what are the various basic rules for drawing the resonance structure. So we'll not go in much detail, but we will see what are the basic rules. Firstly, never break the sigma bond. right? The sigma bond skeleton should remain unchanged in all the canonical forms. So it's only the pi bond or the lone pair that are rearranged, or if you are having charges, so it's only the charges, the lone pair or the pi bond that's delocalized, right? So never break a single bond. So if you break the single bond, you're breaking the basic carbon skeleton, right? Second, never exceed an octet for second row elements. Right? In case of first row element, the first period element is a duplet that's followed, and in case of first row element we have only hydrogen and helium, so we don't consider the first row. But in case of the second row elements, that second period elements, you don't have to exceed the octet, right? Why we don't have to exceed the octet? Because they don't have the vacant d orbitals to accommodate more than 8 electrons. For third row period, you may exceed the octet because they can accommodate the extra electrons in their d orbital. Right? So whenever you are drawing the resonance structure, always remember that number one, never break the sigma bond, right? Sigma bond should remain intact. They should never be broken. Second, when you are dealing with second row elements, especially carbon, nitrogen, oxygen, and fluorine, remember that they have only 8 electrons to be accommodated in the outermost shell. You cannot have more than 8 electrons. For example, nitrogen cannot form 5 bonds, because if it's forming 5 bonds, then you're violating the rules of Valence, right? The nitrogen can only form 3 bonds, but the elements in the group in the period below, so element below nitrogen, that's phosphorus. So phosphorus can form 5 bonds because it has the d orbital, right? So for second row elements, you must have the conscious that you don't have to exceed the octet. Next, we'll say what are the types of arrows that we are using in the resonance structure, right? So curved arrows are used to convert one resonance structure into another, right? So there are two types of curved arrow: the double-headed arrow or the normal arrow, and second is the fishhook arrow. So normal arrow, this is the double-headed arrow. It's also known as the normal arrow. That always indicates when you are shifting 2 electrons, right? Also, that indicates the heterolytic cleavage of a pi bond, right? Or it also indicates the shift of a lone pair, right? So whenever you are moving 2 electrons, either they can be the 2 electrons of a pi bond, or they can be the 2 electrons of the lone pair. So whenever you are moving 2 electrons, then you have to make use of this curved normal arrow. That also indicates heterolytic cleavage. And in case you are only shifting 1 electron, especially in case when you are shifting an unpaired electron, then you have to make use of this fishhook arrow. And this fishhook arrow, that single-headed arrow, right? This also shows the homolytic cleavage. So what's a homolytic cleavage and what's a heterolytic cleavage? These are basically 2 types of bond cleavage. So when you break a bond in such a way that one of the atom gets 2 electrons and other atom gets none, then in that case, this cleavage is known as heterolytic cleavage, right? But when you break a bond in such a way that each of the atom carries 1 electron, then such type of cleavage is known as homolytic cleavage, right? So in case when you are breaking the bond in a homolytic manner, that means you are involving one unpaired electron, then you have to use this fishhook arrow. But when you are making use of 2 electrons shift, then you have to use the normal arrow, right? And lastly, whenever you are showing the resonance structure, since resonance structures are not real, make sure that you use this double-headed single line arrow mark, right? So whenever you are using this arrow indicates that anything which is on the end is not real, that's imaginary, right? So whenever you are describing the resonance phenomenon, or whenever you are dealing with the resonance structures, always make sure that you use of this arrow, right? That's resonance arrow. So now we'll move towards the basic patterns, right, for drawing the resonance structure. So there are basically 5 basic patterns. We'll discuss them one by one. The first pattern is the pattern of allylic carbocation, right? So it's allyl, as I've explained later, right? So allyl system is a system in which there's a double bond, and to this double bond we have an sp3 carbon here, right? So it should be a single bond next to a double bond. So this is allyl group, and this carbocation, that's allyl carbocation, right? So for an allyl carbocation pattern, always a C4 system when we have a positive charge next to a carbon-carbon double bond, right? So since we are discussing about the resonance system must be conjugated, if these two conditions are fulfilled, then this pattern will be called allyl carbocation pattern. Alright, so whenever you are using this allyl carbocation pattern, so we make use of one curved arrow pattern, right? So in this case, you have to shift these pi electrons towards this positive charge here. In this way, you can convert one resonance form to another, right? So simple, a curved arrow that will start from the pi bond and will shift towards the single bond, right? So by this movement, you can say, no, in the next resonance structure, there will be a single bond and there will be a pi bond, right? And this positive charge would have shifted here, right? And when you have to reverse the condition, just draw the arrow from this pi bond and shift towards this single bond. So you can interconvert these resonance structure into one another. So in case of this allyl carbocation, this specific example what we have taken, the resonance hybrids are equivalent. They have equal contribution, right? So whenever two resonance structures are equivalent, they have equal contribution, right? So on what basis we are saying them to be equivalent is on the basis of this carbocation. So if you just check, this carbocation is primary here, and similarly this carbocation is also primary here. So since both resonance structures have primary carbocation, means that both resonance structures are equivalent, and since both are equivalent, so they all both contribute equally, right? So the resonance hybrid has equal charge over all of the carbon. So suppose if it has a half formal charge on this carbon, then that will have a half formal charge on this carbon as well, right? So we are not discussing about central carbon because it's clear that it's doubly bonded in both of these structures, right? So whenever two resonance structures are equivalent, means they're equal, then it means they will contribute equally towards the original resonance structure, right? So just for example, we take another example. So in this case, we have just extended the conjugated system, right? Since this is allyl carbocation pattern, means that we must have a positive charge, and this positive charge must be next to a double bond, right? So what we do is that in order to convert one canonical form to another, what we do in this pattern is that we shift this pi electron towards this positive charge here. So once we shift, then we get a positive charge here. So this is the next canonical form, and you can see here that we are using this resonance arrow, right? Now in this case, in the first case we had a primary carbocation, but in the second case we have a secondary carbocation. Now these two resonance structures are not equivalent. In the previous case, both the structures were equivalent, but in this specific case, both are not equivalent, right? So in this case, this is primary and this is secondary. Now, since secondary is more stable carbocation, right? So if a canonical form is more stable, it has more contribution. So this will contribute more, and this will contribute less. Again, if we shift again, if you can see here again is an allylic pattern. So here we have a positive charge, and next to this positive charge is a pi electrons. So the next contributing structure you can make is just to move the arrow from the pi system to the single bond. So here you can see here we have a positive charge here. So you have three contributing structures, right? The first contributing structure is a primary carbocation, second one has a secondary carbocation, third has a primary carbocation, right? So among these three, the first structure and the third structure, they are equivalent. Why they're equivalent? Because they are forming primary carbocation, but the second structure is forming a secondary carbocation. That's why this is more stable, and a canonical form that's more stable, that will contribute more, right? So this will contribute more, that will have greater weighted average, and these two will be equivalent and they will have equal weighted average, right? So again, let's take another example. Again, this is an allylic system. If just carefully, just don't consider that as a benzene. Consider this is a positive charge, and next to this positive charge is a pi system, right? So this is an allylic system, allylic carbocation. So what we do is just when we have to draw the resonance structure, just shift the pi electrons towards the single bond, right? So when you draw this arrow, what will happen in the next canonical form? So here we will get a positive charge, and here we will get a double bond. So double bond and a positive charge. Now this has become an allelic system. So this is positive and this is pi again. So you shift the pi electrons to this side. So here we'll get double bond, and here we'll get a positive charge again. So this has become again an allelic system, right? So you will shift the pi electrons and get a positive charge here, and now it has become the allelic system, right? So double bond and a positive charge, right? So just you have to see the common pattern. So whenever you have a positive charge and next to that positive charge is a double bond, whatever that be the system, doesn't matter, right? So in that case, this pattern is called the allelic carbocation pattern, and you just have to shift the pi bond towards the positive charge. The second pattern for drawing the resonance arrows is when there is a pi bond between atoms differing in electronegativity, right? So you may have a double bond, you may have a pi bond between carbon and oxygen, you may have a pi bond between carbon nitrogen, carbon sulfur, or nitrogen oxygen, sorry, that's a duplication, right? So you can have a double bond between these two. So double bond is a pi bond actually, right? So in such cases, groups like these can have one more resonance structure which have completely polarized pi bond. And when you have completely polarized pi bond, ensure that the negative charge should be on more electronegative atom, right? So although they are not conjugated system, right, the ionic resonance structure is valid for giving the electron deficiency at the less electronegative atom, right? So if you draw that in this way, so what will be the resonance pattern? You have to draw the arrow in such a way that pi bond is shifted towards oxygen, right? So if that's shifted towards oxygen, so oxygen will be negative and the carbon will be positive. So in this way, although the system is not conjugated system, it's not conjugated, but this will result in formation of ions, right? That will result in formation of generation of formal charges. So carbon will be positive and oxygen will be negative, right? So in this way, we'll get a carbon that's electronically deficient, means carbon is electrophilic, and this oxygen will be nucleophilic because it will be getting a negative formal charge, right? Moreover, the ionic resonance structures can enter into another conjugated system to make an exclusive contributor to resonance hybrid. So in case if your carbonyl system, or if such systems are attached to a resonance form, are attached to conjugated system, for example aromatic system, then they contribute towards the resonance hybrid. Let's take a few examples that will make this understand better. So for example, this is simple carbonyl system, right? This system is not conjugated. So what happens that when you have to draw arrow in this case, you have to shift the pi bonds towards the more electronegative atom, right? So arrow should not be going towards carbon because the negative charge on oxygen is more stable. So this is the arrow pattern. So in case you have carbonyl system, the arrow should always go to the electronegative atom. So here we get this contributing structure here, right? So here we have single bond on oxygen with oxygen negatively charged, and here we have a carbon with positive charge here, right? So this is the resonance form that's indicating this is a resonance hybrid. But suppose if this system is not conjugated, right? So this is not proper resonance. But if this carbonyl is a system, is part of the conjugated system like this one, so what happens that in order to draw the resonance structure, right, just draw the arrow towards the oxygen or any electronegative atom here. So here we'll get a positive charge on carbon and a negative charge on oxygen, like that, right? So in this way, what happens that we have to shift the electron towards this positive charge, just like we did in the allyl carbocation pattern, except that this is a carbonyl system, right? So if you shift this electrons towards this positive charge will be here, then again this electron will shift here, and then we'll get a positive charge here, and then this pi electron will shift here, getting a positive charge here, right? So in this case, in this way, this positive charge will be delocalized over all of the system. So this is the system, this is the pattern when you have a carbonyl, when you have a pi bond between atoms of differing electronegativity, right? So next comes our third pattern. So in case we have a positive charge next to a lone pair, then how we can draw the resonance structure, right? So this forms the conjugated system once we have a positive charge next to a lone pair. Alright, so previously in the allylic system we had a positive charge next to a double bond, and now we have a positive charge next to a lone pair. Alright, so lone pair can donate 2 electrons. So since we are moving 2 electrons, we have to make use of this full head arrow. Alright, so we are using normal arrow. So this arrow will go towards the positive charge here, so we'll get a double bond. And since this oxygen has given us 2 electrons, so it will get a positive charge right here. And in order to convert the structure back, just shift the electrons back towards the oxygen. So you'll get the positive charge back on carbon, and the oxygen will get its lone pair back. Right? So this is a form of conjugated system, and what happens that empty p orbital of this positively charged carbon, it conjugates with the p orbital which is carrying the lone pair. So always remember that whenever you have a lone pair, whenever you have a positive charge, whenever you have a negative charge, or whenever you have a free radical, that always resides in a p orbital. Since we have a p orbital here, then this p orbital, this positive charge is residing in the p orbital. Similarly, this lone pair is also residing in the p orbital. So both of these p orbitals are parallel to each other, so they overlap and form a pi bond. Right? That's why this lone pair is easily shifting between them. It's not simply shifting, actually the lone pairs are being shared with this p orbital, because this p orbital having lone pair that's in parallel position to overlap with this p orbital that's empty. Right? So in this way, so whenever you have a positive charge next to a lone pair, so in order to draw the resonance structure, just shift the lone pairs toward the positive charge. Right? So you get a double bond here and positive charge on oxygen, and you can convert the structure back by simply pulling the pi electrons back on oxygen. Right? So this is a way to show the relocalization of electrons here. Another example, so instead of having oxygen, we are having nitrogen here. The same example, so we have here a lone pair and a positive charge. So what will happen? So we will shift the lone pairs towards the direction of this positive charge. So by the end, we'll have a double bond here and a positive charge on nitrogen. So if you have to convert the structure back, just pull the pi electrons back on nitrogen. So carbon will get a positive charge and nitrogen will be relieved with a positive charge here. Right? Similarly here, so we have a cyclic system. System is not conjugated, but you can see easily that in order to convert this form, so what we do is that we shift the pi electrons towards oxygen, so carbon will get positive and oxygen will get this negative charge here. The third pattern is that when we have a lone pair next to a pi bond, right? So in case of the allylic carbocation here, we had a carbocation here, but in this fourth pattern, what we are having electron-rich system, right? So we are having lone pairs here, right? The fourth pattern has a lone pair next to a double bond, so this is like an allylic system. This is a allyl system with a lone pair containing group, this allyl carbon, right? So this lone pair can be a neutral atom, can belong to a neutral atom, or this lone pair can be a negatively charged ion, right? So lone pair has 2 electrons, the negative charge has 2 electrons as well, so you can have a negative charge here, also you can have a lone pair here, right? So these are the systems like CH2 double bonded CH, and next there is an X. So X can be like a halogen, can be anything, right? So you can have system like this one. So here you can have carbon, or you can have any other atom. So we have a double bond. It can be double bond between carbon carbon, can be double bond between carbon oxygen, carbon nitrogen, nitrogen nitrogen, etc. And there we must have some atom which have either negative charge or a lone pair. So these are the examples of such system. Right, so in order to draw the resonance arrow, what we'll do, so the direction of arrow will be from rich center, so the lone pair is electron rich center, so you'll move arrow towards here, the lone pair will be shifted towards the single bond, and this pi bond will shift towards this carbon. Right, so we'll get a double bond here, and this carbon will get the negative charge. You get negative charge here, and we'll get a double bond here. Similarly, when we have a system like this one, so this lone pair negative charge will shift between this carbon and carbon single bond here, so X and carbon single bond here, and this pi bond will break and the electron will shift toward the oxygen. So in this case, the lone pair or the negative charge is being delocalized. Right, so initially it was on X and later on that will be on this terminal carbon. Consider the example. So here we are having a carbon with 2 electrons. It's in the form of negative charge, so direction of arrow will be, so we'll make use of 2 arrows, 2 curved arrows. So in the previous case we made use of just 1 curved arrow, but in these structures we have to make use of 2 curved arrows, right? So how? So one electron, this electron pair in the form of negative charge lone pair, that will shift on this carbon single bond, and the next pi bond will shift on this carbon. Right, so for drawing this resonance structure, we have made use of 2 curved arrows. Right, so by the end we'll have a double bond here and a negative charge here. Similarly, we have a carbon with negative charge, and it's bonded to a pi system. Right, so what happens? The negative charge will shift here, and this pi bond will be shifting here. Right, just see that in such examples we have to make use of 2 arrows because we have to make 2 shifts. So one is the shift of negative charge, and second is a pi system, because both are electronically rich. So when you're shifting electrons here, because of repulsion, so this electron will be distorted. Right, so we are having this structure, and the next structure you can say that you can just shift pi electrons towards the nitrogen, and you'll get this positive charge on here, and nitrogen will have negative charge here. Right. Similarly, here we have a double bond, right, and next to this double bond is a lone pair. So forget about whatever the system is, right, just identify the pattern. So here we have a double bond, here we have a pi system, and next to this pi system is a lone pair. So what happens? We make use of 2 arrows. So the lone pair will be shifted towards the carbon single bond, carbon oxygen single bond, and this pi bond will be shifted towards more electronegative atom. Right, so here we have oxygen with negative charge, and here this oxygen will get the positive charge. So this is the 4th pattern in which we have a lone pair next to a double bond. Right, the double bond can be between same atoms, it can be atoms of different electronegativity. Now we come to the 5th pattern. The 5th pattern is the benzene ring resonance. It's typical, you might have experienced it a lot. So actually there are 3 conjugated double bonds in 6-membered ring, right? So this is 2 chemical resonance structure we are showing here, and we make use of 3 arrow marks. Right, so in the previous examples, in the initial examples, from pattern 1, 2, and 3, we just made use of single arrow. Right, and in case of the 4th pattern, we made a use of 2 curved arrows. But in case of benzene resonance structures, we have to make use of 3 curved arrow, 3 arrow marks. So you shift the electron here, then here, and then here. So you cannot use just 1 arrow because there is consecutive shifting. Similarly, in case of pyridine, so pyridine just resembles that of benzene, except that it has nitrogen here. So also in case of pyridine, you have to make use of 3 curved arrow marks, like here. So these are the different 5 patterns of drawing the arrows for explaining the resonance structures. For drawing the resonance structures, here is the summary. So we may have a system like a, just magnifying for you. So in case if you have a system in which there's a lone pair next to a double bond, right, then you have to make use of 2 curved arrows. However, when you have a positive charge next to a pi bond, then you have to make use of 1 curved arrow. Right, when you have a lone pair next to positive charge, you have to make use of 1 arrow. Similarly, when you have a pi bond between atoms of 2 different electronegativity, then you have to make use of this single arrow. Similarly, when you have alternating double bonds like that one, right, you have to make use of 10 arrows. And if you if you have a benzene-like structure which is not drawn here, then you have to make use of 3 curved arrows. Right, the basic rules for drawing the resonance structures will remain the same. That is, don't break the single bond, don't exceed the octet for second row elements, and the carbon can't have less than an octet in resonance structure, and like the same way, so don't use positive to positive negative charges because they are specific for the metals, and organic compounds can have 4-point charges of 0, +1, or -1. right? So if you get a resonance structure with a 2 plus or 2 negative charges, then change it. That's wrong, right? And furthermore, the tail of a curved arrow, right, should start from pair of electrons, right? Also, it always points from efficient to efficient. So tail should be always to the electrons pairs and should point out in the direction in which there is a deficiency of electron, right? So curvy arrows are used to show movement of electrons, but they do not involve the movement of atoms. So whenever you're drawing the resonance structures, ensure that your atoms remain at their position, so the position of atoms is not changed. So that's all for today's lecture. Thank you.